Hi, my name is Evan. I'm a rising third-year PhD student advised by Chelsea Finn. Today, I'll briefly overview our work on the exploration problem in meta-reinforcement learning. This is joint work with my fantastic collaborators, Aditi, Percy, and Chelsea. The world constantly changes, so we need agents that can quickly learn new but related tasks. For example, a robot chef should be able to quickly adapt to new home kitchens or recipes. We don't want to have to learn each task from scratch, since this is expensive and highly sample inefficient. Instead, meta-reinforcement learning attempts to quickly learn new tasks by leveraging prior experience on related tasks. During meta-training, the agent gets to train on several tasks, such as different recipes and kitchens, and then must quickly learn a new task at meta-test time. On this new task, the agent is allowed to spend an episode exploring to find task-relevant information, like the locations of the ingredients, and then it must exploit this information to solve the task, such as cooking a delicious meal. A natural approach for learning to both explore and exploit is to directly maximize rewards end-to-end. This approach typically groups together exploration and exploitation into a single long episode, and then learns that with standard reinforcement learning techniques. Unfortunately, this runs into a chicken and egg problem, where learning to explore and learning to exploit depend on each other. In the robot chef example, if the robot cannot currently efficiently explore to find the ingredients, then it can't learn to cook. And if it can't cook, then no matter what happens during exploration, it never cooks a meal and always achieves low reward. And this in turn makes it hard to learn to explore and find the ingredients, since there's no reward signal. Overall, this leads to local optima, which require many samples to escape. Instead, the key idea behind Dream is to avoid the chicken and egg coupling problem by learning exploration and exploitation independently. Then, the main challenge is creating an exploration objective that recovers all and only the task-relevant information. To do this, we assume that we can distinguish all the meta-training tasks from each other with a unique problem ID, which can be realistic in real-world meta-RL problems. Using this assumption, Dream operates in two main phases. In the first phase, it simultaneously learns an exploitation policy and to identify task-relevant information completely independently from exploration. Then, in the second phase, it learns to explore by just recovering the task-relevant information discovered in the first phase. This step doesn't directly depend on the exploitation policy, and so this avoids the chicken and egg problem. More concretely, in the first phase, Dream takes the problem ID, which indirectly encodes all the information necessary to solve the task, such as the locations of the ingredients. But this problem ID might also indirectly encode extraneous information, such as the color of the walls or any decorations in the kitchen. Dream tries to remove this extraneous information with an information bottleneck, while simultaneously learning an exploitation policy that tries to achieve high returns conditioned on the bottleneck representation. In the second phase, once Dream has learned the bottleneck representation Z, encoding only the task-relevant information, Dream can then learn an exploration policy to produce exploration trajectories that encode exactly the same information as Z. In one experiment in our paper, we test if Dream can scale up to challenging exploration problems with high-dimensional states and sparse rewards. In this experiment, the agent needs to go to a correct-shaped and correct-colored object, where the shape of the object is specified by a goal in the agent's state, and the color of the object is specified by the sign. In different problems, the sign says green, blue, or red, and the agent starts on the far side of the barrier and needs to walk around to visually read the sign. Dream learns to optimally explore in this task. It starts on the far side of the barrier, and then it walks around the barrier to read the sign. And in this case, the sign says blue. Once Dream has read that the sign says blue, it can then exploit this information by directly going to a blue key when given the goal of going to a key. Compared with state-of-the-art meta-RL approaches, Dream is the only approach to actually read the sign and therefore achieve high rewards. Existing approaches either optimize rewards end-to-end, which results in the chicken and egg coupling problem, or, like Dream, also optimize separate objectives for exploration, such as Thompson sampling. These approaches avoid the coupling problem, but their exploration objectives do not lead to optimal exploration. Overall, we saw that existing end-to-end approaches suffer from a chicken and egg coupling problem that prevents them from learning sophisticated exploration. Dream avoids this by optimizing separate exploration and exploitation objectives, and creates an exploration objective that recovers only task-relevant information, which achieves really good performance. Thanks for listening to my talk.